Welcome to qnawire.
In this problem, we need to derive for an expression for the velocity of the block and for the angular velocity of the disk upon impact in two conditions. So for letter A, when the impact is perfectly plastic, and for letter B, when the impact is perfectly elastic. So I have here a sketch of the problem. So block A with mass m is initially falling with a velocity v1. When it has fallen a distance h, the chord becomes taut and an impulse is produced, causing the uniform disk with mass m, capital M, center O, and radius r to rotate at an angular velocity omega 2, and for block A to have a velocity of v2 after the impact. So we can start by getting the expression for the velocity of block A, v1, as it falls before the chord becomes taut. So since it fell a distance h, it has zero initial velocity. Hence, v1 is equal to the square root of 2gh. So that's our equation 1. Now, applying the principle of impulse and momentum and taking the moments about point O, the center of the disk, with the clockwise direction taken as or assigned as positive, we'll have the equation m, so mass of the block v1 times r equals, so m v2 r plus, so I omega 2. So I here, so the moment of inertia, since this is a solid disk, so the moment of inertia is equal to 1/2 times the mass times radius squared. Hence, our equation would be, so m v1r equals, so m v2r plus, so 1/2 mr squared omega 2. Then rearranging the equation, so this canceling r, will have so the equation will be, so m v1 equals m v2 plus, so 1/2 m r omega 2. So this is now our equation number 2. Now for letter A, remember that the condition is perfectly plastic impact. So this means that the coefficient of restitution E is 0. And then we can express V2 in terms of R and omega. So that would be V2 equals, so R omega 2. And then deriving the equation for omega 2 from here, so we'll have omega 2 equals, so V2 over R. So we can have this as our equation 3. Now, so substituting equation 3 and 1 in equation 2, so we'll have m square root of 2 gh equals, so m v2 plus, so 1/2 m r, and then replace omega 2 with v2 over r. So simplifying this one, so we'll have this becomes square root of m square root of 2gh equals, so we can factor out v2 in the right hand side of the equation. So this would be v2 times m plus 1/2 times the mass of the disk. So from here we can get v2. So v2 is equal to, so m times 2gh over, so m plus 1/2 m. So further simplifying that, specifically the denominator, so we'll get v2 equals, so that would be 2m square root of 2gh over 2m plus m. So this is our expression for the velocity of the block. Now for the omega 2, so equation 3 gives us omega 2 is equal to v2 over r. So we just have to multiply our v2 by 1 over r. So omega 2 would be simply 2m square root of 2gh over, so r times the denominator 2m plus m. There. Now for letter B, the condition is perfectly elastic impact. So which means that E is equal to 1. Hence, so using the equation for the coefficient of restitution, so we'll find, or we'll have the equation VB2 minus VA2 equals, so negative E times VB1 minus VA1. So VA1 and VB1 are the velocities of the block and disk respectively before impact. And VA2 and VB2 here are the velocities of the block and the disk respectively after the impact. Okay, so VB2 so this will become VB2 can be expressed in terms of R and omega. So that would be R omega 2, then minus VA2 here is actually V sub 2, then equals, so our E is 1, so negative 1 times VB1 here is 0, so 0, and then VA1 is actually equal to V1. There, so this will give us, so R omega 2 minus V2 equals V1. So this is our equation number 4. So substituting equation 1 and equation 4 into equation 2. So we'll have m times square root of 2gh equals, so mv2 plus 1/2 times the mass of the disk times square root of 2gh plus v2. So this will become, so m square root of 2gh equals, so mv2 plus, so m square root of 2gh over 2 plus 1/2 mv2. So we can put into one side all terms with square root of 2gh, and then that's on the left hand side, and then on the right hand side we can have the terms with or multiplied with v2. So simplifying this will become m minus 1/2 mass of the disk times square root of 2gh. So I factored out square root of 2gh, and then the right hand side will be m plus 1/2 times the mass of the disk, then v times v sub 2. So I factored out v2 on the right hand side. So from here we can get the expression for v2. So v2 is equal to, so simplifying the terms in the parentheses, since one has fraction, so that will become 2m minus m, capital M, times square root of 2gh over, so in the denominator, 2m plus capital M. So this is now our expression for the velocity of the block if the impact is perfectly elastic. And then for omega 2, so we can get we can use equation 4 and substitute the value of the expression for v2. So we'll have omega 2 equals, so v1 plus v2 over r. So I just solve for omega 2 from equation 4, and then replacing v2 with v1 and v2 with their respective expressions. So we'll actually get, so square root of 2gh over r times, so 1 plus 2m minus capital M over 2m minus, plus capital M. So simplifying this, so we'll actually get so square root of 2gh over r times, so 4m over 2m plus capital M. So that's our expression for the angular velocity of the disk after the impact.